Figure 1 shows a sketch of part of the curve with the equation y equals g of x, where g of x is equal to the modulus of 4e to the power 2x minus 25, where x is a real number. The curve cuts the y-axis at point A and meets the x-axis at the point B. The curve has the asymptote y equals k, where k is a constant, as shown as figure 1. Part A. Find, giving each answer in its simplest form, I, the y-coordinate of point A. So at point A here, I know that's where it intersects on the y-axis, so I know that x equals 0 at that point. So if I substitute that in to my equation, g of 0 equals the modulus of 4e to the power 2 times 0 minus 25. E to the power 0 is 1, multiplied by the 4 is 4. The 4 minus 25 is minus 21. And when we take the modulus of minus 21, we get 21. So the y-coordinate of point A is 21. Let's now move to part II. So we want the exact x-coordinate of point B. Now we know at point B, that's where the the y-coordinate equals 0. It's where it intercepts on the x-axis. So if I take my function and make that equal to 0, so 0 equals the modulus of 4e to the 2x minus 25. Now the modulus sign here has no impact at all. We don't need to worry about that. In order for it to equal 0, the inside has to equal 0. So the 4e to the 2x minus 25 has to equal 0. So that we can take the modulus of 0, which will be 0. Adding 25 to both sides, dividing both sides by 4, taking the natural logarithm of both sides, and dividing both sides by 2. We get this. But one thing that's useful to note here, to make this a little bit simpler, is that these are both square numbers. And we've got a power of, or rather we've got a coefficient of 1/2. Now using the laws of logarithms, I know that I can take this power half and move that as a power. So I could write x equals ln of 25 over 4 to the power of 1/2. And the power of 1/2 means the square root. And given that they are both square numbers, we can square root them easily. The square root of 25 is 5, the square root of 4 is 2. So my answer for part II is ln 5 over 2. Then for part III, we need to find the value of the constant k. So k is the asymptote. Well, I think the easiest way to think about this, we can see that our curve goes up, up, up. So as x gets smaller and smaller and smaller, becomes more and more negative, it's tending towards this value of k. So let's think about this function and what happens when we make x more and more negative. Oops. So we've got the 4e to the 2x minus 25. So as the x becomes more and more negative, what happens to e to the power 2x as x tends towards really big negative numbers? Well, it tends towards 0. If we think about what the e to the power x graph looks like, it just looks like this, doesn't it? This is the e to the power 2x. So as x tends towards really big negative numbers, this graph tends towards 0. So this tends towards 0. So therefore, the 4e to the 2x is going to tend towards 0. So this will tend towards the modulus of minus 25. And the modulus of minus 25 is 25. So k is 25. Right, so let's move to the next part. The equation g of x is equal to 2x plus 43 has a positive root at x equals alpha. Part B, show that alpha is a root of that equation. So g of x is equal to 2x plus 43. 43 is roughly about here, so 2x plus 43 is going to look something like this. And we can see that they're going to have a positive root here. Now, simultaneous equations for where these two graphs intersect. So 2x plus 43 equals the modulus of 4e to the 2x minus 25. Now, at this point here, at the positive root, we know that this modulus had no effect whatsoever because it's the positive root. So we don't need to worry about the modulus signs at all. Right, I now need to rearrange this equation so it looks like this. So I want to introduce a logarithm to it. So that's making me think, make this e to the power 2x as the subject. So I'm going to add 25 to both sides. I'm going to divide both sides by 4. Then take logarithms of both sides. And then divide both sides by 2. And there we go. That's what we needed to show. We are then told that the iterative formula, given there, can be used to find an approximation for alpha. Part C, taking x0 as 1.4, find the values of x1 and x2, giving your answers to 4 decimal places. So first of all, if I substitute 1.4 into this iterative formula, so I'll get half ln of 1/2 times 1.4 plus 17. If I type that into my calculator, I find I get 1.4368 to 4 decimal places. To get x2, I'm going to use the exact same iterative formula, but instead of substituting the 1.4, I'm going to substitute the answer, or the 1.4368. So on my calculator, a half of ln of 1/2 times answer plus 17, and I get 1.4373 to 4 decimal places. And then finally, part D. By choosing a suitable interval, show that alpha equals 1.437 to 3 decimal places. So my suitable interval is going to be the lower bound, which is 1.4365, and the upper bound, which is going to be 1.4375, And I'm going to look for the sign change in the solution, in the equation that corresponds to alpha. Remember that alpha came from me taking the 2x plus 43 and making it equal to the modulus equation. So alpha was the root of this equation. I'm looking for a sign change, so I want this to equal 0. So let's put everything to one side of the equation here. So I'll get 4e to the 25, 4e to the 2x minus 68 minus 2x is equal to 0. This is a equation that now equals 0 that corresponds with the alpha. So therefore I can substitute my intervals into this. So 4e to the 2 times 1.4365 minus 68 minus 2 times 1.4365. So let me put that into my calculator. Just bear with me. And that gives minus 0.11, so a negative. We're now going to do exactly the same thing with the upper bound. So let me just go back to my calculator and change the lower bounds to be upper bounds now. And I get positive 0.03. So we have a sign change. Let me now write my usual sentence. So sign change in the continuous function therefore there must be a root in the interval. All numbers in the interval round to 1.43723 decimal places.